Today's problem is to discuss the designing of LRU cache. So, LRU cache means it's a least recently used. Recently used. That means we will have a cache and it has a limit. For suppose we were given a limit of 4 records. That means we can save only 4 records in that cache, and we will be having a plenty number of inputs. For suppose our input size is 10 records, but our cache size is 4. So we need to implement the LRU based on this limit. LRU means least recently used. What I mean is we'll have a cache system where, for suppose 10 records are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 records we have. Initially, when we insert a one record, it will be in the cache 1, and 2 it will be in the cache, and 3 it will be in the cache, and 4 it will be in the cache. Then we are reached limit 4, and when we input 5 in this, the cache needs to contain only maximum of 4 records. The fifth one will be like out of limit. What we need to do, we need to remove the least recently used one. What is the least recently used one? This is the least recently used one. We need to remove this. As we can see in this picture that this is the least recently used, but programmatically how we do, we will discuss about that later. But the concept of least recently used is removing the record which is used least recently. So 1 is used least recently because 4 is the one which we inputted least most recently. So this is the list. It'll go off, and we can insert a record of 5 such that we will still maintain a cache size of 4. And now we want to access 3. Now 3 is here. What is so 3 is already there, so 3 should be in the cache. We don't have to remove any element from the cache, but here the concept of least, as we are using a 3 or getting a 3 should go on the top of the cache. 3 should no longer be here, it should be on the top of cache. So the order will be 3, 5, 4, 2, because this is the one which we recently used, and 3 will never be 3 will no longer be on the lower part because we have used it recently. So we should keep on refreshing the cache in such a way that the least recently used ones should be down and the most recently used should go on to the top. So to keep track of this thing, we can't do the manipulation and keep track of the least recent and most recent in one data structure. So we'll have to use one more data structure list so that we'll maintain the order of that. So how we will maintain the order? So initially one will be here. Let me erase it and we can do it again. And this is a cache, and this is a cache, and first record went here, and the second record went here, and 3, third record went here, and 4, fourth record went here. This is good now. And then 5, we don't have a limit, but 5 is there, but we don't have limit here. So what is the least recently used one? This is the least recently used one. So we need to pop that up and pop the same from the map and insert into the cache. And now we want to access 3. So this 3 should go to the front. The order we are maintaining here is 3 should go to the, this is the least recently used. So the most is going here. So 3 should go to the most recent position. What is the most recent position? This one. So 3 should go here, 5 here, 4 here, and 3 is nowhere, 3 move to here, and 2 is here. So we can't make it a whole over here. So for this purpose we will use the linked list so that we can easily dismantle the node from the middle of the list and attach it to the front. So for this tracking purpose we'll use the doubly linked list, so that we will have a track of the previous element, previous nodes as well, to attach to the next element, and to um, have the link properly. We will use the doubly linked list here to maintain the list. At the same time, here we will have a cache system, and this reference, if it is in the middle, for suppose we are using a list, this whole needs to be like, we need to shift all the elements. 4 will be here, 5 will be here, 3 here, but then this will become an order of n operation. To avoid that, we will have a reference to this node in this cache. So to have a reference to this node in the cache, what we do, the record number will be the key and corresponding the node will be the value. So corresponding node will be the value, so that we will have a reference of this node here. We can straight away delete this node and link this to this, and this one can be added to the front, so that this will be the most recently used and this will become a least recently used one. Next time when we want to pop it, we can pop it up. The addition of elements in the W linked list, we always add. Here in this case I just shown like 1 2 3 4 5, but in the real case scenario this will be initial node will be 1. When we add one more element, initially head will be pointed to this, tail also pointed to this. When we add a 2, we will add that 2 to the head, so that this will be in order of one operation, and we just assign head to this and tail still will be this. Whenever we delete an element, this is the least recently used one. So the least recently used will always stay at the tail part, so that we just can remove that and assign tail to the previous element. So for this simplicity we will use doubly linked list, and adding the records will always be on the head side, and we'll keep track of the tail end with the pointer tail. And how we will delete the nodes in the middle, because we will have a reference in this cache key value pair. The value is the node and key is the record. So this is the concept. We will code this out now. So as we have discussed earlier, we will be using the dictionary and the doubly linked list combination of these two data structures to implement the LRU cache. So initially we need to define the node, how we want the node to be. How we want the node to be. So the node will have a previous pointer and the next pointer, and it will have the key value as well, because in our problem we were given that put int x and y. X is the key and y is the value, so we'll just keep track of both key and value of that particular node in that same node. So how will be the node definition? This is the node definition. We will have a key and value, previous and next. And in the constructor, whenever we instantiate this node, we will be creating a new node with the value x and y, and the previous and next pointers will be null. That will be an empty node. So what I mean is, we'll create this node. This will be the value x, and this is the previous, and this is the next, this is the value. So how we will do, public node int x and int y. So the key is x, value is y, previous and next pointers will be nulls. So this is the definition of the node. Now we will start implementing the LRU now. We will have this LRU here. Let's suppose we have defining the LRU as LRU cache. What we will have? We need to have a head, we need to have a tail, and we need to have a dictionary and the capacity as well. So that the LRU cache, whenever instantiate the LRU cache, we will be instantiating with the default capacity. These are all the properties that we need to have. These are all the properties private to this LRU cache, we can declare them as private. One head and one tail. We will have a dictionary. So the constructor will get the whenever we instantiate that will be a limit. We will be giving a limit. That limit will be equal to the capacity, and we will be instantiating the dictionary. As we have discussed earlier, we will be having the node as a value to have the reference to the values in the nodes in the linked list. So we have two methods, get and put methods. What is the get? So the get will have when you get an element, first we need to check whether that element is in the cache or not. If it is in the cache, we will have to move it to the front. If it is not in the cache, we need to add to the map and to add to the linked list as well in the head part. For suppose that is for put. If suppose if we want to get an element, if it is not in the map, we need to return -1. That is the problem statement. If it is there, then we need to move that node to the front. So that is what I meant. So what is the check? If this map contains this key, then what we will do? We will create a node. Sorry, not creating a node. We will get the node. I mean, the value of this particular key will be the node. So that is the map of X. What we need to do? We need to make it to the front. So we will define a separate function, move to front. I'll explain this function later, but what does this do is it just take out the node and put it in the front. Move to the front and just return the value, node dot value. Okay, if it doesn't contain, then just return -1. That is the get method. What is the put? It just gives us the key value pairs. So put public void, it doesn't return anything, so it's a void. It takes int x and int y. These are the key value pairs. Now what are the conditions? If it contains x, then we get the node, and node dot value will be the value which we are passing, that is y, and we just move that node to the front. So that is the first condition. If this map contains this key, then you just extract that node as value of this key and move this to the front. That is what we just did in the get method. And if at all the key value is a different one, we need to update the value which is already present in the map. So you just have to update the value of this node to this y. That is one condition. Now, if it doesn't contain the key, and there are again two things, is the capacity is equal to the map dot count, and if it is not, if the capacity is equal to the capacity limit that is equivalent to the dictionary records count, then that is one case. We need to remove the least recently used one that present at the tail, and then add the xy, put xy, right? So the check is so this is the if case, so we will go to the else now. What is the check? If map dot count equal to capacity, we just have to remove whatever is there in the tail, because tail contains always a least recently used one, and extract the, let me call it as node to be removed, a tail, and point the tail to the previous node, that is tail dot previous, and just make the node to be removed dot previous equal to null, so that we will lose track of this null, and node to be node to be removed null, we make it already null. Done. This is one. When capacity, when it is not equal to that, we just simply add it, right? So we will create a node with that value, and if that is the first node, that means head is null, we just have to point that node both head and tail. Okay, if that is not the first node, just like a simple linked list addition, node dot next equal to head, and head dot previous equal to node, and head equal to node. So the newly added node will become a head now, and we just have to add that to map, the simple one. The only thing that is left is we need to define move to the front. Moving to the front is a separate function now, and we have a node there. So again, this is a private one, and we don't have to return anything from here. So move to front of node, this is the node. Now, is it a first node? If it is a first node, you don't have to move anywhere, keep as is. So you do the whole process only when this is not a head. sorry, node. Again, put it in the temporary variable, node temp equal to head, and go till that part. So as we have a reference here, this is a reference node, we can just make node dot previous dot next equal to node dot next. Done. We set up a link there. Now we have few more cases to check. Is that node is the last one? And is there anything after that node? Right? And we need to, because when we move it, we should always keep track of the tail. If it is the end part, then we need to see if we are moving the tail part, that is the node is tail one, we need to shift the tail to the previous one, right? So the tail would become now node dot previous. We set the node tail now properly. I think that's it. We remove the node and we need to make that node, that we need to move that node to the front, so the head thing is there, right? So head dot previous is equal that node, and head dot previous would become this node, and head equal to node. Now head and tail are set. Yeah. Mm. Okay, so that's it.